For decades, the timeline seemed secure. The universe began in a state of extraordinary simplicity. A hot, dense expansion gave way to cooling matter. Hydrogen and helium filled the darkness. Gravity slowly gathered those elements into the first stars, then into the first galaxies. Each step depended on the one before it. There was no shortcut. Building a galaxy was expected to take time. That expectation was not based on guesswork. It emerged from observations, computer simulations, and measurements collected across generations of telescopes. Every improvement refined the details, but the overall picture remained remarkably consistent. The earliest galaxies should have been small, irregular, and still assembling themselves. Large, chemically evolved systems belonged much later in cosmic history. Then the James Webb Space Telescope began sending back data. Webb was never designed to overturn cosmology. Its purpose was more careful than that. By observing infrared light stretched across billions of years of expansion, it could peer farther into cosmic history than any previous observatory. It would examine the era when the first galaxies appeared and fill in missing pieces of a story scientists believed they already understood. NASA science. Instead, the first observations raised an uncomfortable possibility. Some of the galaxies Webb detected appeared surprisingly bright. Some looked unexpectedly massive. Others seemed to have formed only a few 100 million years after the Big Bang, at a point when many models predicted there had simply not been enough time to assemble so many stars. Several early candidates generated enormous excitement because, if their initial estimates were correct, they represented structures that seemed to mature faster than expected. Later observations revised some of those first claims downward, reminding astronomers that photometric estimates can sometimes exaggerate distances and ages. Even after those corrections, however, a genuine scientific tension remained. The earliest confirmed galaxies still appeared unusually efficient at forming stars compared with many pre-Webb expectations. Wikipedia. That distinction matters. Science does not advance because every surprising measurement survives. It advances because the measurements that do survive force old assumptions into increasingly uncomfortable positions. The question is no longer whether Webb made mistakes. Every major observatory produces observations that require verification. Spectroscopy, repeated measurements, improved calibration, and independent analyses exist, precisely because extraordinary claims deserve extraordinary scrutiny. The more interesting question is different. After the corrections, after the reanalysis, after the excitement settled, why does the tension refuse to disappear? Suppose you were handed the blueprints for a city and told construction would require a century. Roads first, utilities next, buildings afterward. Then someone photographs what appears to be a functioning skyline only 10 years after construction supposedly began. There are several possibilities. The image could be misleading. The timetable could be wrong. Or perhaps the builders worked in ways your blueprint never considered. Astronomers now face a remarkably similar puzzle. The universe does not leave written records. It leaves light. Every distant galaxy is both an object and a message delayed by billions of years. Webb is reading some of the oldest messages ever received. The difficulty is that those messages seem to describe a universe moving faster than many theoretical expectations anticipated. Notice what this does not mean. It does not mean the Big Bang has been disproven. It does not mean Einstein has failed. It does not mean modern cosmology has collapsed. Those conclusions travel far beyond the evidence. Instead, researchers are asking narrower and perhaps more unsettling questions. Were early stars converting gas into new generations more efficiently than simulations assumed? Did dark matter halos grow differently under conditions that no longer exist today? Are observational selection effects making unusual galaxies easier to detect than ordinary ones? Or does the tension point toward new physics that subtly alters the earliest stages of structure formation? academic. Each explanation carries different consequences. Some require only adjustments to galaxy formation models. Others reach into cosmology itself, suggesting that ingredients influencing the young universe may have behaved differently than current models describe. None has achieved broad consensus. That uncertainty is precisely why the discussion remains active in the scientific literature. There is another reason this matters. Human intuition is poorly equipped for cosmic time. The difference between 200 million years and 500 million years sounds enormous because it exceeds any historical experience. Cosmologically, however, those early intervals determined whether gravity had enough opportunities to transform nearly uniform gas into organized galaxies containing billions of stars. Tiny changes in efficiency's first few hundred million years echo across everything that followed. A faster beginning changes more than a calendar. It changes expectations about the birth of stars, the emergence of black holes, the production of heavy elements, and perhaps even the environments in which the first complex structures became possible. The investigation, then, is not about whether Webb embarrassed astronomers. It is about something more fundamental. Every scientific model contains assumptions so familiar that they become nearly invisible. They are accepted not because they are sacred, but because reality has repeatedly allowed them to survive. Webb has begun testing some of those assumptions under conditions no previous telescope could examine directly. And the earliest chapters of cosmic history are proving less cooperative than many expected. The deeper Webb looks, the less certain we become that the universe followed the timetable we confidently reconstructed from much later evidence. The first galaxies may not be breaking the laws of physics, but they may be revealing that our earliest draft of cosmic history was only that, a draft. One explanation appears almost immediately whenever unexpected observations emerge. Perhaps the telescope is fooling us. Astronomy has lived through enough false alarms to make skepticism a professional habit. Every instrument introduces biases. Every survey favors certain objects over others. Every calculation depends on assumptions that can later prove incomplete. Before rewriting the history of the universe, researchers first ask a simpler question. Could the observations themselves be misleading? With Webb, that possibility was taken seriously from the beginning. Many of the earliest headlines relied on photometric measurements. In simple terms, astronomers estimated how far away a galaxy was by measuring its brightness through different infrared filters. It is an extraordinarily effective technique when surveying enormous numbers of distant objects, but it is still an estimate. Dust, unusual, stellar populations, or unexpected emission lines can imitate the colors of much older or much more distant systems. That is why spectroscopy matters. Instead of measuring broad colors, spectroscopy separates incoming light into thousands of individual wavelengths. Hidden inside that pattern are fingerprints left by chemical elements and the expansion of space itself. Those fingerprints allow astronomers to determine a galaxy's redshift with far greater confidence. When Webb's spectroscopic instruments examined several early candidates, some did exactly what cautious scientists expected. A handful turned out to be closer than originally estimated. Others contained fewer stars than initial calculations suggested. Some dramatic headlines quietly disappeared. If this had happened to every candidate, the story would have ended there. Webb would simply have demonstrated that early estimates require careful confirmation, exactly as astronomers already understood. But that is not what happened. After the corrections, enough surprisingly, early galaxies remained that the broader question refused to disappear. Instead of asking whether any unexpected galaxies existed, researchers began asking for so many appeared to be producing stars at remarkable rates. During the universe's first few hundred million years, the discussion shifted, no longer centered on individual record-breaking objects. It became a question about population statistics. One unusual galaxy might simply be luck. 10 unusual galaxies begin to hint at a pattern. Patterns are much harder to dismiss. This is where another possibility enters the investigation. Perhaps the universe did not build galaxies faster. Perhaps astronomers misunderstood how efficiently the earliest galaxies converted gas into stars. That distinction sounds subtle, but its implications are enormous. Most visible matter in the young universe was hydrogen gas. Gravity gathered that gas into halos dominated by dark matter. Inside those halos, clouds cooled, collapsed, and ignited nuclear fusion. Every step wastes material. Radiation pushes gas outward. Exploding stars scatter matter back into space. Supernovae inject energy that interrupts future star formation. Black holes can heat surrounding gas until collapse becomes difficult. Modern simulations include all of these competing processes because nature rarely allows gravity to work without resistance. Yet, almost every one of those processes becomes uncertain under conditions that no longer exist today. The first generations of stars contained almost no heavy elements. Their temperatures differed. Their lifespans differed. Their explosions differed. Even the cooling behavior of primordial gas changed because elements like carbon, oxygen, and iron had not yet been manufactured inside stars. That means researchers are trying to reconstruct an environment that has effectively disappeared from the observable universe. There is no nearby laboratory where those conditions can be reproduced on galactic scales. Everything must be inferred. Computer simulations attempt exactly that. Modern cosmological simulations have become astonishingly sophisticated. They begin with conditions measured from the cosmic microwave background, allow gravity to evolve billions of particles forward through time, and include increasingly detailed models for star formation, stellar feedback, black hole growth, magnetic fields, and gas dynamics. The simulation reproduce much of the nearby universe remarkably well. Galaxies resembling the Milky Way emerge naturally. Large-scale cosmic structure closely matches observations. Clusters, filaments, and enormous voids appear where theory predicts they should. That success makes Webb's early observations especially uncomfortable. The challenge is not that simulations fail everywhere. The challenge is that they succeed almost everywhere except where the universe is youngest. Imagine reconstructing an entire human life from infancy to old age. Every photograph matches your reconstruction. Every school record fits. Every medical record agrees. Then someone discovers authentic photographs from the first week after birth, and suddenly nothing lines up. The problem is confined to one brief period, but it happens to be the period from which everything else develops. That is where cosmologists now find themselves. Several research groups have proposed that early galaxies may simply have formed stars with extraordinary efficiency. Under this view, the basic framework of modern cosmology remains intact. Dark matter still dominates structure formation. Cosmic expansion behaves as expected. Gravity follows familiar rules. Only the astrophysics inside young galaxies requires revision. This would be a substantial adjustment, but not a revolutionary one. Others remain unconvinced. Increasing star formation efficiency solves some observations while creating tension elsewhere. Producing enormous numbers of stars also generates radiation capable of disrupting later star formation. It affects chemical enrichment, supernova rates, and the timing of cosmic reionization. Pulling one thread changes several others. Every proposed solution must satisfy all available evidence simultaneously. That is considerably harder than explaining one surprising image. The situation illustrates something the public rarely sees. Scientific confidence is rarely built on spectacular discoveries. It is built on consistency. An explanation survives only if it solves today's puzzle without breaking yesterday's successes. Webb has not handed astronomers a single mystery. It has handed them a network of interconnected questions, and every possible answer must pass through all of them. before it earns its place in the history of the universe. At this point, it becomes tempting to ask whether the problem extends beyond galaxies themselves. What if the universe did not merely build stars more efficiently? What if the framework describing the growth of the universe's largest structures is missing something subtle? That possibility sounds far more dramatic, but cosmologists approach it with considerable caution. The modern picture of the universe rests on what is often called the lambda-cold dark matter model. It combines ordinary matter, dark energy, and Einstein's theory of gravity into a framework that explains an enormous range of observations: the expansion of the universe, the large-scale distribution of galaxies, the relic glow of the cosmic microwave background, gravitational lensing, galaxy clusters. In many respects, it is one of the most successful scientific models ever developed. That success creates an important dilemma. When new observations create tension, researchers are naturally reluctant to discard a framework that already explains so much. History supports scientific revolutions are far less common than scientific refinements. Most anomalies eventually find their place without requiring entirely new laws of physics. Yet history also offers another lesson. Sometimes the smallest inconsistencies become the first visible signs that a deeper assumption needs revision. Mercury's orbit appeared only slightly different from Newtonian predictions. The discrepancy was tiny, but it survived every correction. Eventually it pointed toward general relativity. No astronomer expects Webb's galaxies to produce an equally sweeping transformation. The comparison serves a different purpose. Persistent anomalies deserve patience, not because they guarantee a revolution, but because they reveal exactly where our understanding is under the greatest pressure. One area receiving renewed attention is dark matter. Dark matter cannot be observed directly. Its presence is inferred through gravity. Galaxies rotate too quickly. Galaxy clusters contain too much mass. Light bends around invisible structures. Across every scale examined so far, unseen matter appears to outweigh ordinary atoms by roughly 5-to-1. Without dark matter, galaxies would have struggled to assemble at all. Gravity acting on visible matter alone would have worked too slowly. Ironically, the same ingredient that makes galaxies possible also influences how quickly they can form. Dark matter creates gravitational wells long before ordinary gas cools enough to ignite stars. Those invisible structures become the scaffolding upon which galaxies eventually emerge. If the scaffolding formed slightly earlier, or if small dark matter halos merged more efficiently, or if dark matter possesses properties that differ modestly from current assumptions, the first galaxies might appear sooner than today's simulations predict. None of those ideas has become the preferred explanation. Each introduces new questions of its own. Some versions of self-interacting dark matter improve certain observations while conflicting with others. Warm dark matter changes the abundance of small galaxies, but often delays structure formation rather than accelerating it. Alternative models must still reproduce the remarkable agreement between cosmological theory and measurements of the cosmic microwave background. Changing one component is rarely isolated. Everything in cosmology is connected. There is another possibility that attracts attention whenever early galaxies are discussed. Perhaps the initial conditions of the universe contained slightly stronger fluctuations than expected on very small scales. The cosmic microwave background provides an extraordinarily picture of tiny density variations, roughly 380,000 years after the Big Bang. Those variations became the seeds from which galaxies eventually grew. Current observations fit theoretical predictions remarkably well. Yet they cannot measure every scale equally. If small fluctuations behaved differently than assumed, gravity might have begun assembling structures more rapidly in selected regions. Again, this is not the leading interpretation. It is one of several ideas being investigated. because Webb has exposed a region of cosmic history where observational evidence was previously scarce. This pattern appears throughout science. Whenever a new instrument opens an unexplored window, uncertainty briefly increases before it decreases. The first microscope did not simplify biology. It revealed microorganisms no one expected. The first X-ray telescopes transformed astronomy by exposing violent processes hidden from visible light. Radio astronomy uncovered pulsars, quasars, and the cosmic microwave background discoveries that were unimaginable when optical telescopes dominated the field. Every major observational advance creates a temporary period during which the universe seems stranger than before. Webb is almost certainly passing through that stage now. The question is whether this period ends with improved astrophysics, or whether it eventually points toward deeper cosmological revisions. Researchers are careful not to confuse those possibilities. The public often asks whether the standard model of cosmology is broken. Scientists usually ask a narrower question: exactly which prediction disagrees with which observation, and by how much? That difference in attitude explains why progress often appears slower than headlines suggest. Evidence accumulates one measurement at a time. Models are adjusted one suspect at a time. Confidence grows one independent confirmation at a time. There is no single observation that forces an entirely new understanding overnight. Instead, pressure builds gradually. One galaxy becomes several become dozens. Independent teams analyze the same data using different methods. Competing simulations attempt different assumptions. Some explanations weaken, others gain support. Over time, uncertainty begins to organize itself. For now, Webb's earliest galaxies occupy precisely that uncertain territory. They are neither catastrophic failures for modern cosmology nor routine confirmations of existing theory. They sit in the uncomfortable middle ground, where science often does its most important work. The observations are strong enough that they cannot be ignored. The evidence is still incomplete, enough that no single explanation has earned victory. And that leaves us facing an older question than any telescope can answer by itself. When reality refuses to match our expectations, are we witnessing an exception? Or are we looking directly at the place where the next generation of understanding begins? There is a tendency to think of scientific progress as a straight line. An observation appears. A theory explains it. New observations confirm the theory. Eventually, confidence replaces uncertainty. Reality is usually far less orderly. The history of astronomy is filled with periods in which better instruments created more questions than answers. Every generation believed it had reached a stable picture of the universe, only to discover that stability depended on seeing only part of the evidence. The Milky Way was once thought to be the entire universe. Then larger telescopes revealed countless other galaxies. The expansion of the universe itself came as a surprise. Dark matter emerged because galaxies refused to rotate the way visible matter predicted. Dark energy appeared when distant supernovae indicated that cosmic expansion was accelerating rather than slowing down. None of these discoveries happened because scientists expected them. They happened because measurements became difficult to ignore. That perspective changes how Webb's observations should be understood. The telescope is not competing against existing cosmology. It is testing it. Every successful scientific theory survives only because reality continues to cooperate. The moment new observations expose a weakness, the theory is not discarded. It is challenged to explain more than it explained before. Sometimes it succeeds. Sometimes it evolves. Occasionally, it gives way to something larger. What makes Webb unusual is that it observes an era where direct evidence has always been scarce. For most of modern astronomy, the first few 100 million years after the Big Bang existed primarily inside simulations. Researchers began with measurements from the present universe, applied known physics, and reconstructed what the earliest galaxies should have looked like. That approach worked remarkably well because there was little direct evidence available to contradict it. Webb has changed that balance. For the first time, observations are beginning to compete with reconstruction. That distinction matters more than any individual galaxy. Imagine trying to reconstruct the opening chapter of a novel after reading only the final pages. You might infer the personalities, the conflicts, and the sequence of events with impressive accuracy. Then someone hands you the actual opening chapter. Even if most of your reconstruction proves correct, the differences become disproportionately important because every later event depends on those earliest moments. The young universe occupies exactly that position. Small differences in the beginning can propagate across billions of years. One of the most active areas of investigation can star formation itself. Most stars do not form in isolation. They emerge inside giant molecular clouds where gravity, turbulence, magnetic fields, radiation, and stellar explosions compete continuously. Modern simulations capture these processes with increasing sophistication, but they remain computational approximations of systems that span enormous ranges of scale. Now place those same processes inside a universe containing almost no heavy elements. Cooling behaves differently. Gas fragments differently. The balance between radiation and gravity changes. Even the masses of the earliest stars may have differed significantly from those forming today. Astronomers refer to these first stellar generations as population 3 stars. None has yet been observed directly. Their existence is inferred because the universe initially contained almost nothing except hydrogen, helium, and trace amounts of lithium produced shortly after the Big Bang. Every heavier element had to be manufactured later inside stars. If population 3 stars were substantially larger than modern stars, they would have burned hotter, lived shorter lives, and enriched their surroundings far more rapidly. That could accelerate later generations of star formation in ways current models are still attempting to quantify. The difficulty is obvious. The very stars most capable of explaining Webb's observations disappeared billions of years ago. Researchers are searching for their fingerprints rather than the stars themselves. Those fingerprints appear in chemical abundances, radiation signatures, and the earliest galaxies' spectral characteristics. Each new observation narrows the possibilities. None provides a complete answer. There is another challenge hidden beneath all of this. Astronomers never observe a galaxy exactly as it exists. They observe light that has traveled for billions of years through an expanding universe. That journey is not passive. Gravity bends light around massive foreground objects. Intervening gas absorbs selected wavelengths. Cosmic expansion stretches every photon toward longer wavelengths. Even the brightness of a galaxy depends partly on how space itself evolved during the light's journey. Extracting physical properties from those observations requires sophisticated modeling at every stage. That does not make the observations unreliable. It means every conclusion carries carefully measured uncertainties. Those uncertainties are shrinking as Webb continues its surveys. Larger samples reduce statistical fluctuations. Improved spectroscopic observations refine distances. Independent research groups repeatedly analyze the same galaxies using different assumptions. Agreement grows where the evidence is strongest. Disagreement becomes easier to isolate where uncertainties remain. This slow convergence rarely attracts headlines. Yet it is the mechanism through which separates genuine discoveries from temporary excitement. Viewed this way, the so-called JWST case begins to look different. It is less a crisis of cosmology than a stress test of scientific confidence. The Standard Model is being asked to explain observations that previous generations could not obtain. Some parts of the framework continue to perform exceptionally well. Other parts require adjustment. Whether those adjustments remain within galaxy formation physics or eventually extend into cosmology itself remains an open question. What is already clear is that Webb has accomplished something few scientific instruments ever achieve. It has forced researchers to revisit assumptions that had quietly become foundations. Not because those foundations have collapsed, because, for the first time, they can be examined directly against the earliest surviving evidence the universe is still willing to provide. If Webb has taught astronomers anything, it is that the earliest universe was probably less predictable than our simplified models suggested. That does not mean it was chaotic. It means that small physical processes, acting under extraordinary conditions, may have produced consequences large enough to remain visible more than 13 billion years later. One of the strongest examples is the relationship between stars and the galaxies that contain them. It is easy to picture a galaxy as a stable collection of stars moving together through space. But galaxies are not static objects. Especially in the first billion years, they were environments of constant construction and destruction. Gas flowed inward through the filaments of the cosmic web. New stars ignited in dense clouds. Massive stars exploded after only a few million years, enriching their surroundings with heavier elements, while simultaneously disrupting future formation. These processes competed with one another. Gravity tried to build. Radiation tried to slow that construction. Supernovae both created the raw materials for future generations of stars and scattered those materials back into interstellar space. The outcome depended on balance rather than certainty. That balance may have been very different in the young universe. Several recent studies suggest that early galaxies experienced highly bursty periods of star formation instead of growing at a smooth, predictable pace. Rather than forming stars at a constant rate, they may have alternated between intense episodes of rapid growth and quieter intervals while gas accumulated again. If Webb is preferentially detecting galaxies during those luminous bursts, the population could naturally appear brighter than long-term averages would suggest. That possibility changes how the observations should be interpreted. Brightness is not always the same as mass. A galaxy undergoing an intense burst of star formation can briefly outshine another galaxy that contains more total stars but is forming them more slowly. Distinguishing between those possibilities requires detailed spectroscopy, improved stellar population models, and observation across multiple wavelengths. Webb is gradually providing exactly those data. Another uncertainty lies with the stars themselves. The earliest stellar populations almost certainly differed from those born inside today's galaxies. Without heavy elements to cool collapsing gas efficiently, theoretical models suggest that many of the first stars may have been significantly more massive than stars forming today. Such stars would produce enormous amounts of ultraviolet radiation, while living only a few million years before collapsing or exploding. If even a modest fraction of early galaxies contained larger than expected numbers of these massive stars, several puzzles become easier to understand. The galaxies would appear brighter. They would enrich their surroundings more rapidly. They would alter the chemistry of later generations of stars, sooner than many simulations currently assume. Yet this explanation introduces another problem. Those massive stars disappear almost immediately on cosmic timescales. Their direct light has long since vanished. Astronomers must infer their existence indirectly from the chemical fingerprints they leave behind and from the ray emerging from galaxies billions of light years away. It is a remarkable situation. Some of the most important actors in the story may never be observed directly. Instead, they are reconstructed from the traces they left inside galaxies that survived them. This is one reason the discussion surrounding Webb has become so productive. Different explanations do not simply compete. They overlap. More efficient star formation, bursty stellar activity, different stellar populations, refined estimates of galaxy masses, improved modeling of dust, selection effects in deep surveys. Each may explain part of the tension without explaining all of it. Science rarely rewards single-cause answers when nature offers several interacting processes. Perhaps the most revealing outcome is not that one theory defeats another. It is that Webb is forcing galaxy formation, stellar evolution, dark matter physics, and cosmology into the same conversation. Questions that were once studied separately now influence one another directly. A revision to early star formation changes expectations for chemical enrichment. Chemical enrichment affects how later stars cool and form. Those stars influence black hole growth. Black holes regulate surrounding gas. That regulation shapes future galaxies. The entire system becomes interconnected. This is why researchers have resisted declaring either victory or crisis. The evidence is too substantial to dismiss. The uncertainties are too significant to ignore. Some of the earliest claims of impossible galaxies have become less dramatic after improved measurements, while other observations continue to push existing models toward higher star formation efficiencies and more complex histories of galaxy assembly. The overall picture has become more nuanced, not less intriguing. That nuance is easy to overlook outside astronomy. Public attention often favors a dramatic headline, followed by a definitive resolution. The universe rarely cooperates with that pattern. Instead, it offers something slower. A gradual accumulation of evidence. A sequence of increasingly precise observations. A steady narrowing of possibilities. And with every new observation, one uncomfortable realization becomes harder to avoid. The earliest galaxies are no longer distant abstractions, reconstructed almost entirely from theory. They have become observable places. Places where long-standing assumptions can finally be confronted by evidence instead of expectation. That transition may prove to be Webb's most enduring contribution. Not because it immediately rewrote cosmology, but because it transformed the first few 100 million years of cosmic history from speculation into investigation. There is a natural instinct to ask when this story will end. When will enough observations have been collected? When will enough galaxies have been measured? When will astronomers finally decide whether Webb exposed a flaw in our picture of the early universe or simply revealed details our previous instruments could not resolve? The answer is less satisfying than a headline. There will probably be no single moment, no press conference declaring that cosmology survived unchanged, no announcement that decades of theory have been discarded. The history of science almost never unfolds that way. Instead, confidence shifts gradually. One observation becomes 10. 10 become hundreds. Independent surveys begin finding the same patterns in different regions of the sky. Simulations improve. Spectroscopic measurements replace provisional estimates. Explanations that once seemed equally plausible slowly separate as some continue matching the evidence, while others accumulate contradictions. That process is already underway. Programs such as JWST, SEERS, and other deep field surveys are expanding the census of galaxies from the universe's first billion years. Every observing cycle increases the sample size, reducing the chance that astronomers have simply been looking at an unusual corner of the cosmos. At the same time, theorists are revising galaxy formation models to account for burstier star formation, changing stellar populations, and the complex interaction between gas, radiation, and gravity under primordial conditions. Some surprises have already become less surprising. Several of the earliest record-breaking galaxies turned out to be closer than first estimated after spectroscopic confirmation. Other candidates survived those tests. Even more intriguing, entirely new observations have emerged. Webb has confirmed extremely luminous galaxies less than 300 million years after the Big Bang, while continuing to uncover evidence that galaxy growth, black hole emission, and chemical enrichment may have progressed with remarkable speed during cosmic dawn. That is the pattern worth remembering. The universe did not become stranger because one extraordinary object appeared. It became more complicated because multiple independent observations began pointing in similar directions without pointing towards a single explanation. There is an important difference between those ideas. One spectacular anomaly can disappear. A consistent pattern demands understanding. Perhaps the most profound lesson has little to do with galaxies. For generations, humanity reconstructed the opening chapters of cosmic history indirectly. We measured the mature universe around us and inferred how its early structures must have formed. It was an impressive achievement, but it was still a reconstruction. Now, for the first time, we are beginning to replace inference with directive observation. That transition changes the relationship between theory and evidence. The earliest universe is no longer merely the starting point of simulations. It has become an observable frontier, and every frontier has the same effect. It exposes assumptions that were previously invisible. Some assumptions survive, others are refined, a few eventually disappear. The uncomfortable part is that we rarely know which category we are looking at while history is unfolding. Future telescopes will almost certainly push even farther. They will detect fainter galaxies, measure weaker spectral signatures, map larger regions of the young universe. Perhaps they will reveal that Webb's tension gradually dissolves as our models improve. Perhaps they will strengthen the case that some aspect of early structure formation still escapes our understanding. Either outcome would represent scientific success, because science is not the defense of existing ideas. It is the continual negotiation between expectation and reality. That is why the phrase JWST crisis may ultimately prove misleading. A crisis implies that knowledge is collapsing. What Webb has revealed is something far more valuable. Knowledge is becoming more precise. Precision is uncomfortable. Every improvement removes explanations that once felt sufficient. Every new observation reduces the space available for easy answers. The deeper we look into the universe, the less room remains for assumptions that have never been tested against direct evidence. The first galaxies are not merely distant objects scattered across the darkness. They are the surviving witnesses of a period the universe has almost completely erased. Their light began its journey before the Milky Way existed in anything like its present form. Before Earth, before the Sun, before the cometry that eventually allowed observers to ask how any of this began. After traveling for more than 13 billion years, that light reaches instruments built by a civilization occupying a brief moment on a single planet around an ordinary star. And instead of confirming every expectation, it quietly suggests that the opening chapter of the universe may still contain sentences we have not learned to read correctly. Perhaps that has always been the deeper implication of astronomy. The farther we extend our vision, the less certain we become that our oldest assumptions were ever seeing the entire picture. The universe has not changed because James Webb looked farther than any telescope before it. Only our confidence has. And history suggests that whenever confidence begins to shrink while evidence continues to grow, we are standing at the threshold of understanding rather than at its conclusion.